Okay, we're going to do a few lessons today. 10.4 and 10.5 are a lot of review of stuff we've done a few times. So I'm going to race through those pretty quickly. Then 10.6 will be on probabilities with geometry, which is, I think, pretty sweet. So let's say a shape has vertices with the points 1, 1, 1, 4, 4, 1, and 5, 5. I'm going to plot those points real quick. 1, 1, 1, 4, 4, 1, 5, 5. Our first step is to classify this shape. This looks like a kite, but I can't just go by what it looks like. I have to actually determine it's a kite. For it to be a kite, these two lengths would have to be the same, and these two lengths would have to be the same. It's pretty easy to see that these two are the same. This is length 3, and this is length 3 just by counting. But finding this length here and this length here, we can't just do by counting because of the fact they have some slope to them that isn't just vertical or horizontal. I don't actually need to find their length. I just have to show that they're the same. So if I try to find the distance from this point here to this point here, I could run the distance formula, which I've written a million times. I'm not going to again. If you don't have it memorized by now, go figure it out. But I can also just check, the change. This is going up 1 and right 1, 2, 3, 4. This is going right 1 and up 1, 2, 3, 4. They're both going to have the same distance because they have the same change. Okay, if I ran the distance formula of this, say I did this right triangle here, and I wanted to find the hypotenuse, I would do 1 squared plus 4 squared. It doesn't really matter what that is, because it's going to be the same on both sides. So this is definitely a kite, because it has two pairs of congruent sides, but those congruent sides are not opposite each other, they're adjacent. So this is a kite. To find its perimeter, now I actually do need to know this length right here. So 1 squared plus 4 squared is really 1 plus 16, which is 17. If I do the square root of 17, so what I'm doing right now is Pythag, right? I'm doing Pythag. And here's 1, and here's 4, and I want to find c. So that becomes 17 equals c squared, so root 17 is c. So this length right here is root 17. As is this length right here, root 17. So its perimeter would equal 3 plus 3 plus 2 root 17s, which is 6 plus 2 root 17. So root 17 plus root 17 is 2 root 17. Sweet. Okay, let's find the area. To find the area, you might not remember this, but we have a formula for how to find the areas of rhombuses and kites. It's 1/2 times the two bases. So we've got to find the lengths of those bases. Let's start with a short one first. I'm going to use Pythag with this right triangle. I know that's a right triangle because those are vertical and horizontal lines. So this is length 3, and this is length 3. It's root 18. And root 18 is actually 3 root 2. So one base, the short base, is 3 root 2. The longer base is going to be, I think, a bit more difficult to find. I mean, luckily this right here, well, that was a weird line it drew. Luckily this right here has a nice clean slope of up 1, right 1. So if I think about how this is going 1, 2, 3, 4, and this is going 1, 2, 3, 4, that's going to be 4 squared plus 4 squared equals c squared. So 32 equals c squared. So the square root of 32, which is actually just 4 root 2, is that diagonal. So the second diagonal, I wrote B, but I wanted to write D. D for diagonal. The second diagonal is 4 root 2. If I do a half times the first diagonal times the second diagonal, well, I'm going to do this in steps. Root 2 times root 2 is just 2. So it's a half times 3 times 4 times a 2, which is 6, 12, 24, 12. The area of this is 12 units squared. That was all very fast, but none of it's new. In fact, I hope you didn't really need to write it down. You just sort of are finding lengths using the Pythagorean theorem or the distance formula and calculating areas and perimeters. Okay, it says find the area and perimeter if each coordinate were tripled. We've done this also. The point 1, 1 would become the point 3, 3 right here. The 0.14 would become the 0.112. 312. I'm multiplying the x and the y values by 3. So I get 312 and 12, 3. This point out here, 5, 5, would come way out here to 15, 15. And the kite would look like this. It's 3 times bigger in its perimeter. So the perimeter is going to triple. The perimeter triples and becomes 18 plus 6 root 17. The area is going to get tripled squared. You take the change and you square it for the area. So the area of this is going to be 81. 9 times 12 is 81. No, it's not. It's 108. I'm crazy. 108 units squared. And that's the main thing from this lesson that they're kind of showing us again. If you triple the coordinates or triple the perimeter, the area gets triple squared. You take whatever the factor was and you square it. Okay? So that right there just covered 10.4 and 10.5, the stuff we hadn't done or kind of skipped over. 10.6 is the new fun one. It's on geometric probability. Now, probability is it's a way to find how likely something is to occur. You calculate it by doing the number of ways a desired event can occur divided by the number of ways all events can occur. And you've done this with dice, and you've probably done this with flipping coins, but with areas or lengths or volumes, it's all the same thing. So imagine there's a spinner, and this spinner can land anywhere randomly. You know, it's some game where you've got that little spinner and you flick it really hard and it spins around and you really hope it lands on your color to win something. If each section is the same size, find the probability that we land in a section that's yellow. Okay, that P of Y means probability of yellow. This is the probability of some event. So find the probability that we land in a Y space. Well, if each section is the same size, there are 2 Ys. That's the number of ways the desired event can occur. And there's 3, 4, 5, 6, 7, 8 spaces total. So the probability of landing in a yellow, a Y section, is 2 in 8. But how would you find the probability here of landing in a Y? See, there are 8 sections, but we're clearly way more likely to land in this space than we are in this space. They're not all the same size. So if you wanted to find the probability of landing in a section that's colored yellow, you'd have to know the area of this triangle and the area of this triangle, and then divide it by the area of the whole entire circle, or do something kind of like that. And that's essentially what geometric probability is. It's finding the length, area, or volume of the desired event and dividing it by the length, area, or volume of all the possible events. So let's start with an example that can be done geometrically or not geometrically. Okay, a traffic light is green for 20 seconds, yellow for 8 seconds, and red for 40 seconds. If you arrive at a random time, what is the probability the light is yellow? Well, you probably recognize that you could just think of this as green is 20, yellow is 8, and red is 40. So altogether there's 68 seconds for one whole cycle of this light. If we're going to come when it's yellow, that's just going to be 8 out of 68, which can reduce to 4 out of 34, which can reduce to 2 out of 17. That's a great way to think about it, just numerically. But some people really prefer a geometric way to view this. Okay, so the traffic light is green for 20 seconds. Let's have this length right here represent 20. I'm going to do this as a distance. There's 20 units. The yellow light lasts for 8 seconds, so less than half. And the red light lasts for 40 seconds, so twice as long as the green one. So if I were to pick a point randomly on this number line, what is the probability that I pick a yellow point? Well, out of the 68 possible units, 8 of them are yellow, so it's again going to be 8 out of 68. We can then take that 2/17 and generalize it and say, okay, what if we came to this light 50 times over the span of a month? Maybe it's on our way to and from work or something. we hit this light 50 times in a month, how many times would we expect to hit a red light when we arrived? Well, the probability of getting a red light is 40 out of 68. If I take 40 out of 68 and multiply it by 50, whatever that comes out to is how many red lights I would expect. So you turn on your calculator, hopefully. Maybe you don't. There we go. 40 divided by 68. The percentage of getting one red light is 58% of the time, so over half the time it'll be red. But if we multiply it by 50, that means if we arrived 50 times, we'd expect to have a red light 29.4 times. You might wonder, how do we deal with a 0.4? Like, how can we get 0.4 of a red light? Here's how I think about that. That means 29 times, maybe 30 times, but it's more likely to be 29 times. Just barely, because 0.4 is a little bit under 0.5. But it's probably going to be 29 times. It might be 30. Okay, that was doing it with lengths. Okay, we just divided lengths. Next we'll divide areas. Although we don't actually need the areas here. Okay, so here's another spinner. We're going to find the probability of the spinner landing in any given section, white, blue, red, or yellow. Well, we could try to calculate like the area of this white section. But we don't actually need to know the area. We just have to know what percent of the circle does it take up. We want to find the percent of the circle. See, the whole number of degrees, the whole possible set of degrees, is 360. And remember how probability is the number of desired ways over the number of possible ways? Well, 360 is the total possible number of degrees we can work with. So say we wanted to find the probability of it landing on in the blue sector. That would be a 360 total possible degrees we could work with. 60 of them are blue. So that probability reduces to 1 in 6, which is actually 16.6 repeating percent. That's a good one to memorize. 1 divided by 6 is just a 1 with a bunch of 6's. 1 divided by 6 is 16.6 repeating percent. Obviously, red is going to be the same thing. White is going to be 100 out of 360, which reduces to 10 out of 36, which is 5 out of 18. I don't know what that percentage is. Is it 40? No. Let's find out. $27. I was way off. 27.7%. Finally, the probability of us getting yellow is going to be, the number was 140. 140 over 360, which is really 14 over 36, which is really 7 over 18. If I were to take all of these percentages, 7 over 18 is 0.38 or 38.8%. If I were to take all 4 of those percentages and add them up, this one plus this one plus this one plus this one, they would all have to add up to 100%. Because the only thing possible is to land on one of these sections. And you might be like, well, what if you land on the line? Oh, okay, then we don't count that as a spin and we spin again. So every spin that counts will be one of those 4 sections. Okay, last one. Find the probability of a ball landing in the green areas, provided the ball's a point at random. This is very important because you can't always assume the ball's falling randomly. Like if this were a big target set up in a field and we were shooting arrows at it, if somebody was really, really good, we wouldn't expect it to just be random. We'd think, oh, they're always hitting their arrows inside that green triangle. So the fact that it's random is different than somebody with skill or some level of competency being at play. There's 2 things we have to figure out. I guess technically 3. One of them is what's going to be on the bottom. What's the total area of the shape on the bottom? Area of the big shape. So we'll save some time counting. There are 13 dots here. 13 dots is only 12 units. Okay, that's an important understanding, like distinction in math. Just because there's 13 dots, there's only 12 units, because between two dots is a unit. So this square is 12 by 12, so the total area on the bottom is 144 units squared. Because that's what 12 by 12 is. Okay, I'm going to find the area of this triangle. How do we do that? Base times height divided by 2. 3 times 3 divided by 2 is 4.5. So the top, that triangle is 4.5. Then we find the area of this parallelogram. How do we do that? Base times height. Well, this base is 3, this height is 2, so that's 6. That's not a whole lot of area. So our probability is going to be 10.5 out of 1 over 144. Not an awesome percent. .3%. Here's what's nice about this, though. Since there's no skill involved, since it's just totally random, these triangles could be anywhere. Like it could have been that this triangle here was placed in this corner, and then this parallelogram was just put like twisted right next to it. That looks like a rectangle, so that's probably not correct, but oh well. It wouldn't matter if the only space occupied was way down here in this corner. The probability would still be the same. It still wouldn't change. I think that's it. Yep. See you next time.